This is the differentiation AP review multiple choice worksheet. We're just going through the first 2 pages here. So we're all these problems are just finding the derivative. All this is from chapter 2 from first semester. So we need to recognize this as something we have to rely on chain rule for. Power rule, it's not going to be able to do it. We can't expand this out. So if we rewrite it using parentheses and rational exponents, we see the need for chain rule. And with chain rule, we have to identify the outside portion and the inside portion, and we take turns with each of their derivatives. So the parentheses, 3 minus 2x to the 1/2, we can treat the parentheses to the 1/2 as the outside portion. And then the inside function is the 3 minus 2x. So we're going to take turns with their derivatives. The derivative for parentheses to the 1/2 is 1/2 parentheses to the negative 1/2. And then we fill what's inside the parentheses. We don't touch what's inside just yet. Once we get done with that, then multiply by the inside portion's derivative. So 3 goes to 0, negative 2x becomes negative 2, and then we just clean this up. Negative 2 and 2 cancel out. We're left with a negative 1, and we bring the square root down to the denominator. Answer choice B. For number 2, again, chain rule here, we're going to bring the denominator up to the top. We can't, if we expanded it, we're not going to get much, we're not going to be able to rely on power rule. There's too many terms in the denominator. So we move the denominator to the top. Again, there's a need for chain rule. So the outside portion is what's outside the parentheses. So 2 parentheses to the negative 3. And then the inside portion is what's inside the parentheses, 5x plus 1. So we multiply, find each of their derivatives. So we do power rule for the outside portion. So we bring down the negative 3, multiply by 2. This becomes negative 6. Then we subtract 1 from this exponent, which becomes negative 4. We fill in what's inside the parentheses. And then we multiply by the inside function's derivative. So 5x becomes 5. 1 goes to 0. And then now we just want to clean up. So 5 times negative 6 is negative 30. We push the parentheses back down to the denominator. But looks like in this case, answer choice B has the form of parentheses in the numerator. But right, so once we're dealing with multiple choice, you're just trying to get it down to a form that you can identify with the correct answer. All right, number 3. We have a problem here where these are 2 individual terms separated by plus or minus, and we can just rely on power rule once we clean up both these terms. So 2 root x becomes 2x to the 1/2. We bring the square root to the top and change it to a rational exponent. And then we do power rule for each term individually. Bring the 1/2 down, multiply by, subtract 1 from the exponent. So 1/2 minus 1 is negative 1/2. For the second term, we do power rule as well. Multiply with a negative 1/2 in front. The 2 negative 1/2 will multiply to be positive 1/4. Subtract 1 from the exponent, so minus 2 over 2, we get negative 3/2. And then we just want to clean this up to a point where we can match with our answer choice. So 4x to the 3/2 is the same thing as 4x times square root of x. Okay, so number 4, this is a natural log term. Whenever we see a natural log expression and we're asked to find the derivative, we always want to explore expansion, right? We want to take advantage of the expansion rules that we have available for natural log to make our derivative step easier. So this is in the form of natural log of a over b, which we can expand into natural log of a minus natural log of b. Okay, natural log of a minus natural log of b. And once we have this expanded out, then we can apply derivative rule for each term. Well, for this we can expand a little further. We can bring the x down in front using the power property. X times natural log of e. Natural log of e goes away. I'm just left with x. So now power rule for this term, and then with this we can apply u prime over u for this natural log term. So x becomes 1, natural log of u becomes u prime over u. The derivative for e to the x is e to the x times 1. Negative 1 goes to 0, divided by the full denominator. and then we have our answer. We just maybe have to get it to a common denominator so that we can make it match our answer choice C. So 1 is the same thing as e to the x minus 1 over e to the x minus 1. Combine like terms in the numerator. We copy the denominator over again. The e to the x cancels out. Okay, answer choice C. All right, number 5. Find the derivative of arctangent of x over 2. And arctangent's derivative is u prime over 1 plus u squared. I'm going to rewrite it as arctangent of 1/2 x. So this is clearly my u value. So we're just following the rule here, u prime. So 1/2 x's derivative becomes 1/2 divided by 1 plus u squared. And this becomes 1 plus x squared over 4. I just want to make it match one of the answer choices. If I multiply everything by 4, I can clean up all these messy denominators and force it into a simpler fractional expression. So if I multiply everything through by 4, 4 times 1/2 is going to be 2. 4 times 1 is 4. 4 times x squared over 4 is just going to be x squared. Answer choice E. Okay, for number 6. We want to find the derivative, but we see y included inside our expression is not a nice function, so we have to go through implicit differentiation, which just means that each time we come across y's derivative, we need to make sure we include dy dx. Okay, so one term at a time. X becomes 1. Cosine of u becomes negative sine of u times u prime, and u prime is the derivative of what's inside the parentheses, so x becomes 1. Y becomes dy dx, and then 0 stays 0. All right, I want to solve for dy dx. Right now, this dy dx is stuck inside the parentheses. I'm going to make this outside term distribute through. So I get 1 minus sine x plus y minus dy dx sine of x plus y. Now that this dy dx is kind of free to move about, I can move the non-dy dx terms to the other side. Well, actually, in this case, I moved the dy dx over to the right side. And then I divided this over. And to make it match one of our answer choices, we can split this up into individual fractions. So 1 over sine minus sine over sine. So 1 over sine is cosecant. Sine over sine is 1. So we have our answer. Just have to kind of rearrange, play with it to make it match our answer choice A. All right, number 7, we want to find the derivative. Again, we got to involve implicit differentiation because we have y's all over our equation here mixed into our in with the x's. And we also need to apply product rule because if we look, x and y are multiplied together, so we can't just do 2 dy dx. We have to go through the product rule here. Okay, so a spelled out product rule for that second term there. But first things is that 3x squared. That 3x squared becomes 6x, and then I'm moving on to my my product rule portion. So f prime g. So 2x becomes 2. G stays as y. F is still negative 2x, and then g prime becomes dy dx. Okay, so we're done with the product rule, done with the derivative for the second term. Moving on to the third term, 5y squared becomes 10y. We need to include dy dx, and then the 1 goes away to 0. So we have a couple of dy dx's in our equation. We're just going to rearrange it. I'm going to leave the 2 dy dx, move the 2 dy dx over to the right side, keep the non-dy dx on the left, factor the dy dx out, divide it over, and I factor 2 out of the numerator and denominator and make it one of these forms. If your initial form doesn't look like your answer choice, you can always multiply the numerator and denominator by -1, and as long as you're balancing numerator and denominator with the same operation, we can sometimes use that to kind of clean up our expression to make it look like our answer choice. All right, number 8. If a point moves on the curve of x squared plus y squared equals 25, Then at the order pair, the second derivative is equal to, okay, so second derivative, but we have y's in our equation. We know we got to go through implicit, and we have to go through this process twice. Okay, so let's find dy dx first. Okay, so x squared becomes 2x, y squared becomes 2y, dy dx. 25 goes to 0. And now we're just going to try to get dy dx by itself, subtract the 2x over, divide both sides by 2y. Clean this up, we have dy dx equals negative x over y. Now, that's our halfway point. We still have to get to the second derivative. So, we have to treat this like quotient rule here. F prime g minus f g prime. So, f prime is negative 1 times g minus f g prime. So, y's derivative is dy dx, all over denominator squared. So, I have my second derivative equation. But dy dx, I can clean this up a little bit, so I'm going to replace the dy dx in terms of x and y. We have an expression for dy dx, so I'm going to replace dy dx with negative x over y. And now I have my equation. It looks a little messy, but we don't have to do too much. We don't have to do too much to clean this up, because it's not asking for the second derivative equation. It's asking for the second derivative value. So once we're here, once we have some variation of the second derivative function, let's just go ahead and plug in our ordered pair. So 0 plugs in for x, 5 goes in for y, so we get negative 5 minus 0 squared over 5, all over 5 squared. This cleans up to be negative 5 over 25, which is negative 1/5. Okay, number 9. Limit as x approaches 0. We have a funny looking expression here. Let's just go ahead and always evaluate the limit. Right? If we evaluate the limit, see what we get. If I plug 0 in for h, I get cube root of 8 minus 2. Cube root of 8 is 2. 2 minus 2 is 0. Denominator is also 0. So we get 0 over 0. And there's something special we can do if we get 0 over 0 with limit problems. We can apply L'Hopital's rule. So L'Hopital's rule says I can take the derivative of the numerator and then separately take the derivative of the denominator. And then the hope is that this will turn itself into an expression that will allow for the limit to be found more easily. Okay. So if I rewrite the numerator as 8 plus h to the 1/3 minus 2, I can go through chain rule there. So bring down the 1/3, keep the parentheses, subtract 1 from the exponent, multiply by the inside function's derivative. So technically I need to do a times 1 here. And then h's derivative is 1. We have a cleaned up expression. Let's reevaluate. So into my new derivative, my derivative expressions, 0 plugs in for h. 8 plus 0 is 8. 8 to the negative 2/3. The same thing as 1 over 8 to the 2/3, which is cube root of 8 is 2. 2 squared is 4, so 4 is in the denominator. The 1/3, the 3 from the 1/3 is also in the denominator, so 3 times 4 is 12. That's all in denominator, so 1 over 12.